Let's talk a little bit more about this type 2 error, this situation where in reality the null hypothesis is false, but we don't reject the null. So even though the null is false, we by chance end up with a sample mean that's not in the rejection region. And so before we're going to look at some calculations that we can do kind of after the test to think about the likelihood of having a type 2 error. But before we do that, we're going to play around a little bit with our critical values and take what we've been doing just one step further. So what we've done thus far in our couple examples here, and here we're going to work with the chopstick example, is that we've built to a z-score for a critical value. So specifically here in our chopstick example where we're dealing with a mean, a hypothesized null of the mean as 10 centimeters, and specifically the 5% significance, it's a two-sided test, and so our z critical value is 1.96. And so what we've done, if I could move this out of the way, is that we've done the calculation starting there, and every time we took a sample, we calculated a z-score. And in fact, we can pull the other one up, but we did one that I think the z-score ended up as negative 1.5, and we didn't reject the null. And then in this case over here in the orange, we ended up with a z-score of 3. and that's all well and good. Now, there's one extra step we can take that can speed up the process when we go ahead and take the sample. And in fact, in these types of production systems, this step is probably likely taken, and so we'll talk a little bit about that here. I'm just gonna minimize that. And that step is to bring the z-score and put it in terms of the sample mean that we're going to take. Okay, so we can take we can pull the z-score and specifically calculate what sample mean is it going to take to be beyond that value. So if we think about a z-score of 1.96, and we can do this for both positive and negative, and we can do that here in a second. But let's think about the positive 1.96. On our distribution of the standard normal, right? We have a sense as to where that is. It's out here, and there's 2.5% beyond that. But what we're going to do is we're going to find out what value is actually associated with that along our distribution of 10. So a z-score, if we were to get a z-score of 1.96, what x bar would give us exactly that z-score? And we know that mu is 10 here in our hypothesis. And then, of course, we need to plug in. We're dealing with the z-score. We know the standard deviation, and we are taking what did we say? A sample size of 100. Yes, 100. Okay, and so all we're going to do is solve for x bar, and that's going to give us the sample mean that would be the cutoff. Okay, and so this is we do 1.96, multiply up by 0.1 over 10 equals x bar minus 10. And sorry, it's a little fuzzy there. Whoa. 0.1 over 10. And so we can do, that's going to be 0.0196 equals x bar minus 10. And so we can now know that, so if we rearrange this, that's going to be x bar is equal to 10.0196. So if we find an x bar, if we take a sample of 100 and we find it beyond 10.0196, we will then be in the rejection region. So really what we've done is transpose this onto the original distribution, or I should say we've gone this way. So we know that this value is 10.0196, roughly 10.02, and that should feel natural, right? So our standard deviation is 0.1, and we're taking a sample of 100. And so there should be some sense as to this is about 2 standard deviations divided by the square root of 10. So that gives us a cutoff line. Now, what does that do for us? Well, let's do the negative 1.96, and you can double check this math, but this is going to be this is going to fall out that it's 10 minus 1.96. Sorry, that's not true. 10 minus 0.0196, which is 9.9804. It's not a 4. Okay, and so now we have two values for which if we take a sample mean and it is outside of these values, let's just write them in here, 10.0196 and 9.984. Did I say that right? Yeah, 90 in there. And now, what does that do for us? We don't necessarily have to do this calculation every time. And that can be exceptionally helpful when, let's say you are working on a big production line. And number one, some of the people taking the sample mean may not have been trained in statistics, so they may not be comfortable calculating that z-score. Or number two, just for the sake of time, we don't have to go and re-crunch that z-score every day or every hour, or however often we are running these samples. We now have, in the simplest case, you can stamp these two numbers up on the wall and say, hey, if you take a sample and it's outside of this window, hit the big red button. And so that's in practice that this is a common occurrence. If you do have to repeatedly sample, it makes a lot of sense to just put it in this term and not have to do the math every time. Now, the reason I bring this up in our discussion of type 2 error is because these values are helpful with understanding the potential chance of a type 2 error. Now, again, type 2 error is something we need to contend with, especially when we have not rejected the null. So now let's think a little bit about our sample we took here in the orange. We found we did the math and calculated a z of 3. Now, again, in this scenario, we don't even need to go through that step of finding the z. We can just say we took a sample and it was 10.03, and that is in our rejection region over here above 10.0196. So we found the value in the rejection region, and so we can go ahead and reject. Now, why does this apply to, or why do we want to think about it in these terms when we want to discuss type 2 error? Well, it can be helpful when we think about type 2 error to think about what are we really saying when we reject the null. What we're saying is that we have evidence to believe that this is not the actual distribution. Right? The null hypothesis is assuming that this distribution centered at 10 is the distribution of the samples that we would get. And what we're saying when we reject is that we have gotten a value that is extreme enough to say we don't think that this is the actual population mean, and so it's not the mean of our distribution of sample means. So perhaps we think the distribution lies somewhere else. Maybe it lies above that, right? And probably if we found some value out here at 10.03, we might think that is a natural place to think the mean is, right? And if the population mean is 10.03, then we would get a distribution centered around 10.03, right? You could think of it as, let's say we hadn't made this hypothesis and we just took a sample. Our best guess would be that the mean is 10.03, right? This is what we did in Chapter 9. We took a sample and we built confidence intervals around it. And so in a similar sense, we're going to kind of do that here when we think about what are the chances that we could have had a type 2 error. So again, as I mentioned before in a previous video, we never know the exact likelihood that we've made a type 2 error, right? When we're setting up our hypothesis or in our process here. In step 2, we're choosing the level of significance, but that's related to type 1 error. So when, for instance, when we reject the null, we know that so in this case, we found a sample that was in the rejection region. We've rejected the null, but we know there's a 5% chance that we would get a type 1 error even when the null is true. In this case, what we're thinking about is, let's say the null is false, and let's put a certain value on it. Again, we don't know what this exact population value is, but let's say it is this 10.03. If that was the case, if the true mean was 10.03, how often would we not reject the original null? How often would we fail to reject the null hypothesis that says the mean is 10 when in fact it is 10.03? And that's a number we can calculate specifically. Okay, so in that scenario, what we're really asking is, again, thinking about this cutoff line, this 10.0196, got a little messy there, this 10.0196, in the scenario where the true population mean is 10.03, how often are we actually, now this is, I should change to a new color. This is getting really murky in here, but how often are we in this kind of brownish area here? Right? Because when the value, if the population mean is in fact 10.03, we are occasionally going to get values that are below 10.0196, and we won't reject the null. Okay, and that's a simple calculation, or a calculation we're familiar with. It's not exactly simple, but we've done these types of calculations, right? And we can find a z-score directly from that, and that is, we can do 10.0196 minus 10.03. Again, we can rely upon our standard deviation of 0.01 and taking a sample size of 100. Okay, and so that's going to simply be, I can crunch this a little bit for us. So we get, and you can double, I realize I'm behind the screen there. Okay, so you can verify my math here, but we're going to get move that up here. We get, what did I find? I found negative 0.0104 over, again, this is going to be, I have an error here. So this is 0.1. So this becomes 0.01. Okay, and so let's, we can just say that's about, actually, it turned out pretty well, that is 1. We'll give it a z-score of -1. You could crunch the exact value there, but yeah. So a z-score of -1, how often is that going to occur? Again, we know, you can look up again the exact values, but that's going to be what, about. So here's the empirical rule at play. What does that mean? That means there's 34% in here, so we know that we have about a 16% chance, right? So 50% minus the 34%, the 34% being between the mean of 10.03 and that 10.0196, which means the other 16% fall below it. So that's what I tried to drop here, was 16%. Trying again. So we know that if in fact if the true population mean was 10.03, we would still fail to reject this null of 10 16% of the time. Okay, and that's about as good as we can do at giving a feel for the type 2 error. And of course, that measurement, or that answer changes if we think about 10.02 or 10.04 or 10 or 97 or something like that. Okay, so it's dependent on which another kind of hypothetical population mean that we're thinking about. So again, we can't do as much of a calculation as we can with type 1 error. Not done wildly often in practice, but it is helpful as far as understanding what we're really saying about this hypothesized null value.